So far in the course, we've talked about multitask learning and meta-learning for supervised learning. And now we're going to start talking about reinforcement learning, which introduces a number of really interesting challenges and also opportunities to do better when you're trying to learn multiple tasks and meta-learn across tasks. In the first lecture on reinforcement learning and multitask reinforcement learning will be by Karol. So I'll let Karol take it away.
All right, welcome everybody. Thanks Chelsea for the introduction, and today we'll be talking about reinforcement learning. It will be mostly a primer, but we'll also talk a little bit about multitask and goal condition around. So this is the first lecture that I'm giving in this course. So I'd like to do a little introduction. My name is Karol Hausman. I come from a country in Europe called Poland that is right here. And I'm not a native English speaker, as you can probably tell by now. So please let me know if there is something that you don't understand. I really care about making sure that everything I say and explain is understood by all of you. So please raise your hand in chat, raise your hand or just write something in the chat, and I'll try to get back to you as soon as I see it. If there is something that you should know about me, is that I really like robots. And I've been working on robots for quite some time now. So during the classes that I'll be giving, the material might be skewed a little bit towards that application. Also, I studied classical robotics first, where I was working on a concept called interactive perception, where basically we're trying to control the robots in a way that will make the perception for the robots a little bit easier. And while I was doing this, I remember going to a talk that was given by a student at that point, Sergey Levin, about deep reinforcement learning, and I got completely fascinated by it. I kind of thought that this is the right way of doing things and the right way of solving things that I was actually working on, and that eliminates these boundaries between control and perception and considers them as one interconnected problem. So after that talk, I got very fascinated, and I completely switched my PhD topic and started working on deep reinforcement learning and continue working on it ever since. So if I have any small piece of advice to you is if you find something like this that you really like and you're really fascinated by it, I would recommend to following that path, because it can be very rewarding. And then lastly, I'm also a research scientist at Robotics at Google, which is part of Google Brain. That's where we try to apply some of the algorithms that we'll be learning about today, and during other lectures, we try to apply them to real robots at scale. So I'll try to bring that perspective a little bit more throughout the lectures so that you can see how some of these algorithms work in practice. All right, so with that, let's first start with why should we care? Why should we focus on reinforcement learning in general? And I would like to pose a question to you to think about. Can you think of an action, and a fully isolated action that doesn't affect the future? And what I mean by that is an action that doesn't have any long-term consequences. So there is the immediate consequence when you perform that action in the real world, but are there any actions that don't have long-term consequences? And I encourage you to think a little bit about this, but in the meantime, I think I would like to answer that I think it's really, really hard. So even an action that seems very meaningless, like for example me tapping my fingers right now, it seems that it doesn't have any influence in the future, but it might be that because I tap my fingers right now, I exerted so much energy, or I exert more energy that I would have if I didn't tap them, and because of that, later on during the day, I will need maybe a nap to get my energy back. And in particular, I would like to show you one experiment that kind of tries to exemplify this concept. And this is an experiment that is often shown in things such as chaos theory or butterfly effect. I encourage you to look some of these up. And basically, it shows a double pendulum that starts from more or less the same initial conditions. So you can see 6 different pendulums right here. This is the same pendulum, just repeated 6 times. And you can see that there's a human hand that starts the experiment, but from what we can tell, it basically looks exactly the same in all of these pictures. And now we start the experiment, we let the pendulum go, and this is recorded in slow motion, and you can see that initially all of the pendulums behave exactly the same. right? So they're indistinguishable even at this point. However, over time, you will be able to tell that all of them perform completely different motions and they're in completely different positions. And this is one of the statements of chaos theory that states that even in a fully deterministic world, or in a world that is governed by deterministic equations, because of the fact that we can't really disambiguate initial conditions, we always have to round it up to certain number that we can actually do the real experiments on. Because of that initial state that is a little bit different and the initial action that is also a little bit different, the final effects will be actually random, even though the entire world is governed by, even if we assume that the entire world is governed by deterministic equations. So there is actually one example of an action that does not affect the future. And this is how we model things in supervised learning. So in supervised learning, we make certain decision, and that decision could be, for example, on what's in the image. In the object recognition case, we're given an image, we have to say, is there a cat in the image? And we'll perform that decision, and we pretend that that decision has no consequences beyond that one action that we just did. So this seems a little, this looks like a very small isolated world that doesn't really adhere to how the real world works. So reinforcement learning tries to deal with this problem and tries to model the fact that every decision we make is actually can actually have consequences long term, and it copes with the problem of sequential decision making. So how the decisions that we make now will influence the future and how it will influence our future decisions. And because of that, because it's such a real world kind of concept, it has many common applications, some of which we'll talk about, such as robotics, language and dialogue systems, autonomous driving, where your actions will influence other agents' actions, and because of that, it will influence your actions again, as well as business operations and finance. So basically, most deployed machine learning systems have to deal with that sequential decision-making aspect. And also, I think we can argue that the fact that we can make sequential decisions is one of the key aspects of intelligence. All right, so the plan for this lecture would be as following. First, we'll get familiar with the multitask reinforcement learning problem. Then we'll discuss one way to solve that problem by using the policy gradient method. And we'll learn about their multitask counterparts as well. Then we'll talk a little bit about Q-learning, which should be mostly a review based on the lectures that you've taken previously. And then we'll talk about multitask Q-learning as well. All right, so let's start with multitask RL. So first, let's introduce some terminology so that we can all operate on the same terms. This should be mostly, I think, review for most of you, so we'll go over this quickly. So if we start from an object recognition, a supervised learning pipeline, it might look something like this, where we are given an image as an input, then that image is propagated through some neural network, a convolutional neural network, for example, and at the end of that network, we're trying to classify what's in that image, whether it's tiger or another animal. One change that we'll make in the reinforcement learning scenario is that we'll sub-index all of the things by time step t. Right? So we'll observe an image on a certain at a certain time step t. That image will then be propagated through our neural network, and then we'll output some kind of action also at the same time step. Now that action will influence our next observation. So we'll then get our next observation OT plus 1, and then we'll need to perform another action based on that observation. Also, as we just said, our actions are real actions in the real world. So we no longer have to decide what's in the image, but we actually have to do something about it. So when we are given an image of a tiger, we, for example, have 3 options. We can run away, ignore, or pet it. And all of these will influence how the world is going to propagate from now on. All right, so to describe this notation, O of t would denote observation at time step t. AT is an action that we perform at the time step. And then we'll describe a policy pi theta, or pi theta that gives us the probability of action given the observation as the policy. So this is the policy that we'll use to know how to act in a given situation. In addition to this, we'll have ST, which we'll call state, and we'll get back to it in a second. And then we also have a fully observed version of a policy, which is pi theta, that gives us actions given the current state. So let's talk a little bit about that state versus observation problem. And I'd like to bring up an example from philosophy. This is known as Plato's cave, where Plato had that idea that we as humans are captured in a little cave, and it takes quite long for us to get out of that cave, and there's like a whole complex philosophy behind it. But the basic idea is that we are captured in that cave, and we don't really get to observe the true nature of things, but instead we just see the reflections of them, right? So in particular, what you can see right here, there's a god right here that is holding the true object that we don't get to see. This is a human, this is us sitting in the cave, and there's this big fire behind us that we also don't get to see, and we only get to see the shadow of the true object that is projected onto the wall. All right, so now using that metaphor, the true nature of objects is the state that we don't get to observe very often. And then the reflection that we get to see is the observation, right? So the observations might be incomplete. It might not have all the necessary information for us to be able to perform the right decision, but the state has everything that we would ever need to know how to act. All right, so maybe a more practical example would look something like that. We're looking at an image, and that image is an observation, and we have to make a decision based on that. But in order to make that decision, we actually might want to know a little bit more. That's what in the image. So, for example, the positions of the objects as well as their velocities. So the state should have all the information that we would need to make that decision, and the observation can be actually quite incomplete. So, for example, there could be an occlusion, there could be a car in front of us, and because of that, we don't even get to see the cheetah. And we'll talk about the problem of not being able to observe everything a little bit later too. All right, so this is our terminology. So let's try to think how we could find a policy. All right, so one way we can do this is to take the knowledge that we have from supervised learning scenario and try to apply it directly to this problem. And this is what we'll be referring to as imitation learning. So in this case, we have that image that goes through the network, outputs actions, and the images that we want to focus on in particular are images that are coming from a camera that was installed on a car, and we'll be recording actions of humans that were actually driving these cars. And this was research done at NVIDIA by Boyarsky et al. In a system called Alvin, where they basically had human truck drivers driving their cars as usual, and they would record all the observations, all the images that the car would see, and the corresponding actions that the human drivers would take. So now what we could do is we could just store all of these and compose a big training data set, and then use supervised learning to train our policy based on that. So if we did that, at the end we'll get our policy pi theta. So this is one way how we could do this. Sorry, 1 second. So the question is, are there any problems with that? So are there any problems with imitation learning with the way how it was done, for example, by the folks at NVIDIA? And if anybody has any ideas, please write in chat or raise your hand. Right, okay. Problems might occur in a new environment, or decisions are independent. We're only capturing observations, not fully observed state. It's not scalable. All right, no idea if a wrong decision is made. Yeah, so one of the problems is, I think these are all really good answers. One of the problems is related to something that we saw before with the double pendulum. So if there's some error and we don't fit our actions perfectly, then the error will accumulate and we'll get into a state that we haven't seen any data. So we'll, for example, the cards will start deviating, and because we are only collecting the data of drivers driving correctly, we wouldn't know how to behave or we are getting off the road. All right, great. So reinforcement learning is trying to model this problem in a more holistic way. So in this case, we have to have some kind of way we need to have some utility that we want to optimize for. So before we could just say, let's just try to optimize our policy such that we repeat the actions that the humans would take. In this case, we have to optimize for something else. And this is where reward functions come in handy. So reward function would be something that will allow us to disambiguate which actions are better and which ones are worse. The reward function would be dependent on the state and the action, and it will have a scalar value that we'll try to optimize. So in the case of driving that we just talked about, a high reward might correspond to us driving safely and smoothly on the road, and the low reward will correspond to an accident, for example. And all of these components, so the state, the action, as well as the reward function that depends on the current state and action, as well as the transition dynamics, which tell us the probability of the next state given my current state and the action that I just took, define so-called the Markov decision process. And this is the framework that we'll be operating in. All right, so let's talk a little bit more about that framework and the goal of reinforcement learning. So our goal is to find the parameters theta of the policy pi theta. And that policy takes observations as inputs and outputs actions. These observations actually are a result of some underlying state that we don't get to see. And then that state, together with our action, produce the next state according to this transition dynamics, the probability of S prime given S comma A. That results in the next state, which then produces the next observation, which is then fed into our policy, and we get to produce the action. All right, so this corresponds to a probabilistic graphical model that looks more or less like this, where we have various connections here. So, for example, the connection between the observation and action is our policy pi theta. And the connection between the current state and action that connects these two to the next state is our transition dynamics, P of st plus 1 given st and at. So there's an important thing to note here, which is that if you look at this probabilistic graphical model, the probability of the current state only depends, or on the next state, only depends on the current state and the current action. It's completely independent of the states before that and the actions before that. And this is known as the Markov property. So basically, what we mean by that is something like that. Let me just try to draw on this. So we see that given our S2 and A2, S3 is known, and this is conditionally independent of S1, for example. So this connection is not there, right? In addition to this, which we'll learn a little bit later in the course, there's one other random variable here, which is dependent on the current state and action. And this is the optimality variable. Let's call it big O1. And this is related to the reward function at the time step. So this is a reward of state given state 1 and action 1. All right? And that optimality variable, or that reward, is also conditionally independent of the previous state. It's only dependent on the current state and the current action. So we can also draw it right here, state and action. This will be our O2. And now, given S2 and A2, that's everything we need to know about the to know about the reward. And this is conditionally independent of S1, for instance. So this connection is not there either. All right. So this is the basic idea of the Markov property. It states that the next state is only dependent on the current state and the action, and the same applies to the reward. So if that's not the case, we'll observe a system that is called a partially observable system. So it's not enough, the Markov property is not satisfied, and it's not enough for us to determine what the next state is going to be or what the reward is going to be given the current state and action. And it seems like a fairly obvious concept, but very often it's a little bit more complicated than it appears. And I'll ask you a few questions here. So I'll give you some examples, and I would ask you whether this is an observable system or not, fully observable or not. So here's the first example. We have a simulated robot. This is the robot that you see in the picture here. And this is a robot that performs a reaching task. So it tries to get that end effector, that green dot over here, to the goal position, that is the red dot over here. And it's trying to do this. So it gets a reward 1 when it gets there, and 0 in any other location. And our observation consists of the goal position as well as the positions and velocities of all of the joints. So if you could please answer in the chat, do you think this is fully observable or not? So just say yes if it's fully observable, or no if you think otherwise. Okay, we see lots of yeses. We see some no's. All right, yeah, so the answer is that it's probably fully observable, right? Like we can tell everything about the future, given that we know the position and velocities and the commands that we're sending to the robot. And given the goal position and the current position and velocities, we should be able to determine the reward. Right, let's look at another example. Indiscriminate robotic grasping from a bin given an overhead image. So the task is for this robot that you see in the picture to grasp any object, and to get a reward 1 if the object is grasped, and a reward 0 if it's not. And we only get to see the overhead image from that monocular RGB camera. So again, please answer in the chat. Is it fully observable or not? No, 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 no. Depth is unknown. Yes, depth is unknown. Okay, everybody's answering no. Yes, great, perfect. And one of the reasons for it is, for instance, we can't tell what's the distribution of the weight or how heavy the objects are. So it's possible that even though we get to see exact same observations from, we get to see the two basically the same images, they might consist of very different objects depending on the weight distributions of them that we don't get to see, that we don't get to observe in that setup. All right, so one last example, and this is actually an example from the real world, from a project that we work on at Google, which is a robot that is trying to sort trash, right? So this is the robot that you can see in the image. You can see 3 bins in front of it. There's recyclables, compost, and landfill. You can assume that in the camera, wherever you stand, you can see all of the bins at once, and everything is reachable. And so the robot starts with some trash in the bins, and then it has to sort them. It has to sort them correctly, right? So it gets a reward 1 if at the end of the episode, the object that was previously unsorted is now correctly sorted. Is this an observable environment or not? So is it a fully observable environment? Please answer in the chat. No. Okay, we see quite a few no's. So this is a very similar environment that we have to what we had before. So let's just eliminate the reason that we used previously. So let's just say that we don't really care about the distribution of weight, and let's assume that this is not that big of a problem. Is there something else about this problem that makes it even less observable? If anybody has any idea, please raise your hand. Occlusion, yes, occlusions are possible. Yeah, so there's one other reason. Accurate pose unknown, right? I guess this is the pose of the object. You can't necessarily define materials. Okay, so it might not be clear whether it's a compostable object or not. Yeah, these are all great reasons. So one reason that we actually realized quite recently, which was quite tricky, is that given an image of a robot holding an object above the bin that it's supposed to go to, it's not clear whether you're about to get a reward 1 because you're about to sort that object correctly, or whether you unsorted it in the first place. So it was already in the correct bin at the very beginning, and you're about to drop it into the same bin, in which case you will get a reward 0. So from that state alone, it's not really possible to tell. And this is actually one of the big problems that contributed to making this problem quite challenging. All right, so as we can tell, partial observability can be quite tricky sometimes to determine. But let's go back to the goal of reinforcement learning. So we talked a little bit about the transition dynamics and Markov property. The goal that we are trying to optimize is in the infinite horizon case, we have some stationary state and action distribution, and we're trying to maximize the expected reward in that environment. So we're trying to find the argmax of our policy, of the parameters of our policy, theta, that will maximize the expected reward. Or in the finite horizon case, we are trying to find an argmax and optimize the sum of the rewards from time step 1 to time step t of all the expected rewards that are coming in the future. All right, so we know a little bit about the reinforcement learning setting. So we talk that this course is a lot about multitask learning. So what's a reinforcement learning task? So in supervised learning, if you recall, a task was defined by a data generating distribution. So P of X and P of Y given X, as well as the loss. In reinforcement learning, a task will be defined by a few more terms. So first, a task will consist of a state space. So these are all the states that we can enter. The action space, so all the actions that we could take. The initial state distribution. The dynamics, so probability of S prime given S comma A, as well as the reward function. And it's important to note here that all of these define a Markov decision process, and this is much more than just a semantic meaning of a task. So you can have a task that semantically means, or you can have two different tasks that are doing semantically the same thing, but they're still considered different tasks in the reinforcement learning sense. All right, so let's go through some examples of task distributions. So, for example, in character animation, we can have different tasks where we try to learn different maneuvers. So for example, we can have this little stick figure that is trying to learn how to spin kick, how to cartwheel, how to run and backflip. And in this case, the reward function would vary across these tasks. We can also do a character animation where the character that is shown in the picture is trying to put on a shirt. And here the shirts might vary, as well as the initial states. So the initial state distribution might vary. We might start with a different shirt, or the shirt might be partly on already. And the dynamics will vary quite a bit as well, depending on which shirt you're trying to put on. So these are different tasks, even though the reward is the same. We only get the reward when the shirt is on, but the dynamics and the initial state distributions will vary. Another example would be multi-robot reinforcement learning. Here we have 3 different robots. So here the state space will be different for all of them. The action space will be different as well. The initial state distribution too, as well as the transition dynamics, even though all of them can be trying to perform the same tasks. All right, great. So we talked a little bit about what is a task in reinforcement learning view, but we can actually have an alternative view. We can augment our state a little bit, and we can we here will denote S bar as the original state that we had. And we can add a task identifier to that state. So we'll just append that to our state vector. The task identifier called ZI, which tells us that we are in task I. So this is the original state, and we augment it a little bit. So in this case, the task that was originally defined like this, the multitask setup could be defined as a single task. So in this case, that task would be defined by all of the union of all of the tasks that we are considering. So in terms of the state space of that new multitask task will consist of the union of all the state spaces of all the tasks, the union of all the action spaces, the mixture of the initial state distribution for all of the tasks, the transition dynamics, and the reward. So there's an alternative view where a multitask reinforcement learning problem is still a one Markov decision process. All right, so in terms of the goal of multitask reinforcement learning, it would look exactly the same as before, except we will augment our state with this task identifier, ZI. And that ZI could be many different things. So it could be a one-hot task ID that tells you which task you're in. It could be a language description, or it could be a desired goal state. So for example, an image of what you're trying, what I want you to achieve. In this case, the goal state would be corresponding to a state that we want to reach, SG. And this will be referring to as goal condition RL, which is a special case of multitask reinforcement learning problem. What could be a reward in that case? So it could be exactly the same as before, depending on the task, we'll be getting different rewards. Or for goal condition RL, the reward could be a distance function that tells us the distance between our current state as bar and the goal state as G. Right? And we're trying to minimize the distance, so the reward will be the negative distance. There could be different distance functions that we can use for this, such as the Euclidean distance or a sparse reward. So you only get a reward when you match the state exactly, otherwise you get 0. But we'll talk about this a little bit more later too. All right, so one question you can ask is, if it's still a standard MDP, a Markov decision process, then why can't we just apply standard RL algorithms? And the answer to this is, yes, you can. You totally can. But very often we can do much better than that. And that's what we'll learn about in this course. All right, so are there any questions about the multitask reinforcement learning problem?
I have one quick question, which would be easy to answer. So is the main point you're making with adding Z sub I to the state that in a single task RL problem, this would just be trivially like part of the context of the overall problem, but this gives you, adding the Z sub I, you have a way to sort of embed many tasks in some slightly higher dimensional state space. And you're going to talk about how to solve this problem non-trivially, by methods other than using RL.
Right. So ZI, yes, I think that's a correct intuition. ZI just makes the entire MDP observable again. It basically tells you which task you're in currently, and regardless how it's represented, if it's one hot or goal image or something else, it disambiguates fully which task you're trying to do. And that's what allows you to cast it as a single MDP, as a single reinforcement learning problem.
Cool, thanks.
All right, there's another question. If the tasks don't belong to the same environment, then can we still consider under the same MDP? Yeah, that's a really good question. I think usually we wouldn't do that. I think we can still consider them as separate MDPs, but it is possible to phrase them as a single MDP as well, where we just consider the transition dynamics as the union of all of the dynamics of both environments, and the same applies to the state space and the action space. All right, great.
Sorry, one more question if you don't mind. What's the significance of your distinction between the optimality variable and the reward? Is that easy to answer why there's a difference there?
Yeah, so this is a little more tricky, and we'll talk about it in 2 weeks, I think. We'll have a full lecture on that.
Cool.
All right. All right, so we specify the problem. Let's look a little bit at ways to solve it. So we'll talk about the policy gradient method, and how we can change it to be a multitask method, and how it works. So to start, I would like to tell you a little bit about the anatomy of any reinforcement learning algorithm. And they usually consist of 3 stages. There is a stage where we generate samples. We can do this by, for example, running our policy. There's a stage where we try to fit a model to estimate the return, and the stage where we improve the policy. And different algorithms would implement these boxes in different ways. So for example, to fit a model to estimate the return, what policy gradients would do, it would just sum all of the rewards that you got in the current rollout. This is also referred to as Monte Carlo estimation. The different Q learning methods would allow you to would try to fit a Q function to your returns, and this would be something that would represent the future returns. And model-based methods would try to estimate the transition probability of P of S prime given S, A. Then in terms of improving the policy gradient method would try to optimize the objective that we care about directly and apply the gradient to it, and we'll learn about it in a second. Q learning methods would try to maximize the Q functions that was already learned, so find the action that maximizes it, and that's the action that you would want to perform. And for model-based methods, one thing you can do is, for example, backpropagate through the model and optimize directly for the policy. So in this lecture, we'll focus mostly on model-free RL methods, such as policy gradient and Q learning, and you'll learn more about model-based RL methods, I think in the next lecture or maybe the one after that. All right, so before we talk about policy gradients, I would like to bring up one more concept, which is the on-policy versus off-policy reinforcement learning. So in the on-policy reinforcement learning, the important distinction is that the data that we are training on comes from our current policy. So we can only use our current policy to do rollouts, to actually see how they work, and then we can use that data to update our policy. On-policy data is compatible with pretty much all reinforcement learning algorithms. And it also means that we can't reuse data from previous policies. Right? So you can only use data from the policy that you're currently learning. That's why it's on policy, or learning on the policy that you're actually executing. For off-policy algorithms, the data can come from any policy. It actually doesn't even have to come from a policy at all. It can be some data that was collected by humans, or by some engineered script or something like that. It only works with specific RL algorithms, and we'll learn about that too. And it can be much more sample efficient because now we can reuse all of the old data as well. We are not restricted to the data that we currently see, but we can use data from other tasks or older data. All right, so in this part of the lecture, we'll be talking about policy gradients. And in policy gradients, we'll be staying on policy. So we'll be only using the data that comes from the current policy. All right, so policy gradients try to directly optimize the objective that we care about. So the objective that we care about, which we talked about just a few minutes ago, is the expected sum of rewards. Right, so this is depicted here. We are trying to find the argmax of that, where we are trying to optimize the parameters theta of our policy. And one term that might be a little unfamiliar to you is this term right here, the tau. And that tau is nothing else than that, let's just write it right here, P of theta of tau is the joint probability distribution of all the states and actions, which can be then factored as this probability of the initial state times our policy pi theta of the action A1 given state S1 times the transition probability P of S2 given S1 A1 times the policy pi theta of A2 given S2, and so on. And that at the end results in a joint probability distribution of actions and of all the actions in all the states. So you're trying to take the expectation under that trajectory distribution that is dependent on our parameter theta. This is the parameters of our policy. They influence what kind of trajectories we'll see. And we're trying to maximize under that expectation the sum of rewards. All right, so we'll refer to that objective as J of theta, right? So the objective is J of theta. So we're just rewriting this here again. And because this is an expectation under trajectories, what we can do is we can approximate it with samples. So what that would look in the real world was we would take our current policy, roll it out, so just run it a bunch of times and generate a few trajectories, for example, 3 trajectories like that. And then we'll get rewards for these trajectories. So let's say the top trajectory will get the top reward, the middle one will get some medium reward, and that one at the bottom will get 0 reward. Now to evaluate our objective, we can just sum over samples from our policy. So we can sum all the rewards for each one of the trajectories and then do an average across all of these trajectories. This is just to evaluate the objective. So now given a policy, we can fairly easily say how good it is. All right, so now that we know how to evaluate it, let's try to see if we can improve it. What can we do to actually directly improve our policy? So we have our objective J theta. And here we'll do a little shortcut in notation where we'll say that R of tau is equal to the sum of all the rewards that we'll get in the trajectory. So because tau corresponds to the trajectory, R of tau would be the full return that we get, the sum of all the rewards for that trajectory. All right, since we are taking the expectation under tau, we can write that expectation as the integral of pi theta tau R of tau d tau, which would mean that we need to integrate over all the taus, all the potential trajectories. So now let's try to take a gradient with respect to that objective. So the gradient, if we just apply directly, would look something like that. We have an integral of the gradient with respect to theta of our pi theta r, pi theta of tau, r of tau, d tau. And that would mean that we need to integrate over all the trajectories, which is completely intractable. Right? So this is a very tricky objective, but there's a single identity that is called, that is often referred to as a log trick, that turns out to be very useful here. So let's try to derive this real quick. So let's write the following. Gradient with respect to x of logarithm of f of x. Right, let's just try to estimate what that gradient is. I just kind of made it up, and let's see where we get from there. So this would be equal to 1 over f of x. Right, this is just the gradient of the logarithm, times the inner gradient, which would be the gradient with respect to x of f of x. Right, I just took that gradient. So now what we can do, we can multiply both sides by f of x, and we will get something like that. We would get, so the right side, I'll write on the left side right now. So we will get grad x f of x would be equal to, we just multiply both sides by f of x, would be equal to f of x times grad x log f of x. All right, so we have that little identity right here. And you can see, and this is, that we didn't even talk about reinforcement learning here. Here we are just trying to show a mathematical truth. And this says that this has some familiar terms. So we have this, let me just change the color real quick. We have a term right here that looks very similar to a term right here. Right? So I also put this identity here in the slide so that you can see it in the PDF that is on the website. And this is the observation that we just made. So the gradient of f of x, or the gradient of pi theta, is the same gradient that we see right here. So let's just replace it with the identity that we just derived. So here, just our f of x right here got transformed into pi theta of tau. Right? So instead of x, it's a tau, and instead of f, it's a pi theta. Right? So we just replace that according to that identity. And now we have an equation that can be actually rephrased as an expectation again. So now, because we have an integral over d theta, over d tau, sorry, over trajectory, so d tau. And inside that integral, we have the term called pi theta of tau. We can say that this is the expectation under the trajectory distribution tau of grad log pi times r tau, r of tau. All right, so so far we said that we are trying to optimize that objective j of theta. The objective is fairly easy to evaluate, it's right here. And if we want to take the gradient with respect to it, we can do it by doing that expectation and evaluating that term under that expectation. All right, so you can see that there's a lot of taus in here. So let's bring back the definition of what tau is and see how it actually corresponds to our actual policy. All right, so we have our pi theta of tau is equal to this. And this is the joint distribution of all our states and actions, and this factors as the initial state distribution and times the policy plus times the transition dynamics. Yes, well, there's a question. Can you explain how does this trick solve the tractability problem? Yes, we'll get to it in just a second. All right, so we have our pi theta of tau. Now, if we take the logarithm on both sides, we see that something like this happens. We have our log pi theta of tau, and now we just replace all the multiplications using the fact that the logarithm of a product is the sum of the logarithms, and we end up with an equation like that. And now you can see that we can replace the log of pi theta of tau with the equation that we just derived right here. So let's do that. Let's swap that in. So if we do this, we can now see that it has all the familiar terms. We have the initial state distribution, we have the policy distribution, and we have the transition, the model of the transition. And we have to take gradient with respect to theta of the entire thing. This is the gradient that comes from here. All right, so now if we take the gradient with respect to theta, the initial state distribution does not depend on theta. This is not something that we can control. That's given to us as part of the task. So the gradient with respect to theta would be 0. And the same is true for the transition dynamics. So we don't get to control this. This is not dependent on our policy. So the gradient with respect to parameters of the policy theta would be 0. All right, so what we end up with is then something that looks like that. This is just basically crossing out the terms and putting everything together. The gradient with respect to our objective is equal to an expectation under our trajectory distribution tau of the sum over grad log pi and the sum times the sum of all the rewards. All right, cool. So we derived our gradient that we can actually apply to try to make our policy better. So now there is a question, how does this solve the tractability problem? So basically this question can be translated to how can we evaluate that policy gradient easily? So you can recall that we can evaluate the objective fairly easily by approximating the expectation over trajectories by just samples over these trajectories, right? So remember that picture that we talked about where we had 3 different trajectories and we can just average across the samples. So we can apply exact same trick right here as well. We have the exact same expectation. This is expectation under the trajectory distribution tau. And we can take the average, so we can basically sample our policy, get our trajectories, and then average across the samples. Right? So if we do that, then now we don't really have to take that integral that was so intractable. We can just approximate our expectation with samples, which is what we do very, very often in machine learning. And now all of the other terms are actually very easy to evaluate for us. We know what log of pi is. This would be the logarithm of the output of our policy. And we can also sum all the rewards. So now if we wanted to actually make it into an algorithm, we could just take that gradient and apply a gradient ascent algorithm to it and improve our policy this way. So now if we go back to our little diagram of how reinforcement learning algorithms work, we generate samples right here. Let me switch to a pointer. Generate samples right here. This is the approximation of the expectation of samples. So this is our orange box. We fit a model to estimate the return right here. So in this case, this is just the Monte Carlo estimation of our returns. We just sum all the returns that we actually got from the trajectories. And to improve the policy, we do the gradient ascent procedure where we are applying the gradient that we can evaluate. We know how to evaluate it right here, and we apply it to our policy parameters. And because of that, we can get a better and better policy. Right, so all of these things, if we put them together, we can implement a fairly straightforward algorithm called reinforce. And this is kind of the basic policy gradient algorithm. The way it works is as follows. We sample a bunch of trajectories from our current policy by just running it. So we produce the trajectories. Then we evaluate our gradient. So we basically do the equation that we just talked about right here. And then we apply that gradient to our parameters using the gradient ascent procedure. And we keep doing that over and over again. So we apply that gradient, we get a policy that is a little bit better, then we sample from that policy and do this iteratively over and over until the policy gets better. All right, so there's one interesting fact about this entire procedure, which is that it's actually fairly similar to a maximum likelihood model that you would use for imitation learning. So if you recall that little example that we had with drivers, where we were collecting states and actions and collecting a training data set and doing supervised learning on it to get our policy. The objective that you would actually try to optimize to achieve that would be a maximum likelihood objective that is well known from standard supervised learning. There's a question, where represents the multitasking reinforced? Yeah, we'll talk a little bit about the multitasking in 1 second. So you can see that the imitation learning objective would look like a maximum likelihood objective that is right here. Right? This is just maximum likelihood of our actions that were taken by humans. And the policy gradient objective is actually extremely similar if you look at it. So the first term right here is pretty much exactly the same, except these are the samples from our current policy, and these are the samples from the trajectories that we got from the humans. But we have this multiplication, this additional multiplication that multiplies it by the sum of the rewards. And that means a few things. So first, that means that we can make these two algorithms completely equivalent if we set a reward function to a very specific reward function that says that every time you succeed at something, you will get a reward, the sum of rewards 1. And if you fail at something, the sum of rewards would be 0. Then both of these algorithms look exactly the same. It would just mean that you would have to do imitation learning on your current policy, on your current rollouts, update your policy according to it, and then do rollouts again, update the policy using only the positives, and so on. The other thing to notice is that because this objective is so similar to a supervised learning objective, actually all of the things that you learn about multitask learning algorithms can be readily applied here too. So everything that you learn about multitask supervised learning can be very, very easily used in this setting as well. All right, so a little recap of what just happened. So we derived a way to approximate the gradient with respect to our objective. And we showed that it's very similar to maximum likelihood. So what does that actually mean in practice? So if you didn't pay attention and you didn't follow all the math, what does this algorithm actually do? So what it does is the following. We roll out a bunch of trajectories according to our current policy. You can see them in here, let's say 3 different trajectories, and they get different rewards. So we sum the rewards for each one of these trajectories. Now what policy gradient is trying to do is trying to make trying to shift the distribution of our policy to make the good stuff, the stuff that got really high reward, more likely, and the bad stuff less likely. So basically, if you got a high reward, we'll maximize that likelihood of those actions, and the bad stuff will make it less likely. We'll maximize it less. And if the reward was 0, we won't do it. We won't do anything with it, because if you multiply, if this is equal to 0, that's sum of the rewards, then the gradient will be equal to 0 as well. So if you didn't succeed, if you didn't get any reward for the current task or for the current rollout, you want that won't contribute to the gradient. So basically, that entire policy gradient procedure simply formalizes the notion of trial and error. We'll try some stuff, and then we'll increase the probability of good stuff and reduce the probability of bad stuff. And this is what reinforced algorithm does. All right, so to summarize the policy gradient procedure, we know how to take the gradient with respect to the objective, and there's a few pros of policy gradients. First, it's very simple, so we can easily combine them with existing multitask and meta learning algorithms. But there's also quite a few cons. So first, the gradient that we produce right here is a gradient of quite high variance. All right, so the reason for this is there's multiple reasons, but one of the reasons is that that reward here could vary from trajectory to trajectory, and you would need a lot of rollouts to actually estimate the entire expectation here. So there's a few ways to deal with this. For example, usually in practice, people subtract a state-dependent baseline from this. This is a very common way to kind of subtract from the magnitude of those rewards so that it's a little bit more normalized and the variance is not as high for the gradient. And this is what is usually used by all algorithms in practice. The other con is that it requires OnPolicy data. So in particular, if you look under this expectation here, you see that the expectation is under the trajectory distribution that comes from our current policy, pi theta of tau. So we cannot really reuse existing experience to estimate the gradient. This is a strict OnPolicy algorithm. There are some ways to deal with this by using, for example, importance weighting, but this comes with its own set of problems and produces high variance gradients as well. All right, so that was quite a bit. Are there any questions regarding policy gradients as a way to solve a reinforcement learning task? And we don't have that much time left, so I will maybe take one question. I see that Chelsea replied to some of them, so that's really good. All right, so given that, maybe let's just move on because we don't have that much time. All right, so let's talk about Q-learning. So Q-learning would be an example of an off-policy algorithm that would allow us to use all kinds of data, not only data that come. There's one question: is it true that reinforced doesn't encourage exploration? Yes, that is one of the problems, and there's ways that people deal with that by, for example, adding an entropy term to the rewards, such that you not only try to get to the best solution, but you also try to be diverse. Or sometimes people introduce other tricks such as epsilon greedy and so on. All right, so Q-learning. So it's an off-policy algorithm, so we can use data that comes from many different policies and many different tasks. And we'll start with some definitions. So first, we start with a definition of a value function. I hope that this is a review for most of you, so we won't go into a lot of details. But the value function v pi of st describes the total reward starting from the current state and following the policy pi. Right? So it tries to answer the question, how good is the current state? We also have a q function, q pi of st, at, which tries to describe the total reward starting from s, assuming that you take an action A at the current step, and then you follow the policy pi from then on. And that tries to answer the question, how good is a state-action pair? Right? Both of these are related, and they're related quite closely. So if you take the expectation with respect to your current policy pi of the q function, it will result in the value function v pi of s. And the other thing is that if you know your q function, q pi, you can also use it to improve your current policy. And you can improve it fairly easily if you just set the policy to always pick the action that is the argmax of your current q function. So the action that maximizes the q will be the action that you would want to pick, and this way the policy will be at least as good as the OffPolicy. Right. One other really important equation is the Bellman equation, which describes how this works for the optimal policy. So we have q star now, where star means that this is for the policy that is optimal. And q star is equal to this expectation under the next state of the current reward times the maximum of the q star of the next state in action, where we take the max over the actions. Right, so this is the Bellman equation, and we can use it to perform Q-learning. All right, so I think most of these are probably familiar to you, but we'll go through a quick quiz to kind of make sure that you understand these concepts. So let's say that we have a little stick figure, and that stick figure is dreaming of being a drummer. All right, so the reward that it's trying to optimize is that there's a test coming up in a month from now, and in that test it would need to learn how to play these notes, this sheet of notes. And it will get a reward equal to 1 if it can play it in a month, or 0 otherwise. Right? So this is its reward functions. Its actions are as following. Action 1 is that it can just relax and don't do anything. Action 2 is that it can watch videos of people playing drums and try to learn from that. And action 3 is actually practice drums. Okay. The current policy of our stick figure is to always pick action 1. Right? So the probability of action 1 given the current state is always 1. All right, so here are a few questions. So please answer in chat. What's the value function v pi of st? right? Lots of zeros. All right, great. So a lot of this would require some kind of estimation of, how likely it is that you will be able to play drums if you don't practice. But I think we can fairly confidently say that if you continue with the policy where you don't do anything, you won't be able to play that, to play the drums and get the reward equal 1. Okay, yes, the answer is 0. So what's the Q function, Q pi, of ST80? Now, given that AT is equal A1, right? So assuming that AT is equal A1, what would be that Q function? Please answer in the chat. 0, yep, lots of zeros. Yes, it's exactly the same as the value function. Okay, great. What if you do, what if it's the Q function Q pi ST and AT is equal A2? What would that be? So that would require a little bit of an estimate. Please answer in the chat. So that would correspond to a behavior where you watch a video of someone playing drums once, and after that, you will just continue relaxing and not doing anything. Okay, it's probably a little bit higher than 0, but probably still very, very low. Yeah, there's some answers, 0.01 or something like that. What about if AT is equal A3? So you practice the drums once at the current time step, and then after that, you continue with your current policy pi. It will be probably, okay, yes, it will be something like 0.02. It will be a little bit higher, but still not that high. What about Q star? So what about Q star if AT is equal A1? Please answer in the chat. Right, we don't really see any answer. 0.9. Okay, it depends how talented stick figure is. All right, yeah, it's a really good answer. So it will be probably something really close to 1, right? Because that means that just in the current time step you will relax, but from at the time step all during the days after that you will always be practicing. Right? And then the value function will be equal to 1 because that means that you will be just always practicing, and probably we hope that the reward will be then equal to 1. All right, so this is just a little example that show us how these value functions and Q functions would work in practice. All right, so let's look at quickly at an algorithm that we could implement to actually do Q learning in practice. So this is called the fitted Q iteration algorithm. And it will work like this. We will collect the data set of states, actions, next states, and rewards using some policy. It can be any policy. This is an OffPolicy algorithm. Then we'll set our targets to, according to the Bellman equation, to the reward plus the max of the next Q function. And then we'll try to fit our Q function to these targets. Right? And we can use, for example, an MSE loss to try to do that. All right, and we have our parameters phi here, and our policy will be, or our Q function will be parameterized by a neural network, where as input it takes states and actions and outputs a Q value. One way to do this in a discrete action space is actually have multiple heads where each head corresponds to a different action. Right, we'll take a number of gradient steps S, and we'll perform it over K iterations. So we'll just collect the data set, estimate the Q targets, then try to fit our Q function to these Q targets, and then keep doing that. All right, then we can learn a Q function from that. And as a result, once we have the Q function, we can get a policy from it fairly easily. And that will just correspond to taking an argmax over our current Q function to find the action that maximizes it. And that action will be the action that we should take, and this will be our policy. All right, a few important notes here. So first, we can reuse data from previous policies. So we can use any policy to collect the data, and it should still improve our Q function. It's an off-policy algorithm, and people usually in practice use replay buffers to replay the data that was stored by many different policies. And important note here that this is not a gradient descent algorithm, right? This is a dynamic programming algorithm, and then we are doing a gradient descent in addition to this to just fit our Q function to Q targets. This can be easily extended to multitask and goal conditional RL settings, but not as easily to meta-learning settings, and we'll talk about it in the next lectures too. All right, so I want to give you one more example of how this could work in practice and how we actually use it at Google, but I have to go over this really quickly because we're running out of time. So let's just look at how we can apply this to robotics. And we saw that these targets required a maximum of the Q function, and the maximum is taken over actions. Now, if the actions are continuous, which is the case in robotics, this can be quite tricky. So one way we can do this is to use a simple stochastic optimization algorithm called cross-entropy method. And it works as follows. You would start with the current position of where the robot is, and you will you'll start with a normal distribution with mean 0 and some standard deviation. And then you'll just sample from that distribution, and you will evaluate, you will ask the Q function how good are the actions from that distribution. So you'll sample a bunch of actions, and then you'll query your Q function about it. Then the Q functions will give you, will tell you that some actions are a little bit better than others, and these are here depicted in gray. So this one is a little bit better, this one, and so on. And then you would compute the new mean and standard deviation of the best actions. So right here. And then you can do this procedure again. And if you keep doing that, you can sometimes even do it just for 1 or 2 iterations, you will get more or less the maximum of the Q function. All right, so let's do that. And this was applied to the algorithm called QT-opt, where Q-learning was applied at scale. And this was done at Google, where this was done in a fully distributed setup and applied to a problem of grasping in robotics. So we will start with a data that was stored from all the past experiments. We'll have some buffers that we use for the data that was collected previously, as well as the data that is coming from the robots right now. Then we'll represent our Q function by a neural network. And we'll have separate processes that will do the Bellman update. So they'll just compute the target that we would want to fit our Q function to. This will use the CM optimization that we just talked about. After it's done, after Bellman updaters are done, they will just set a set of tuples with the Q targets as well as the current state in action, and this will be then used to actually to do the mean squared error and update our Q function. So we'll have a bunch of training jobs that are running on GPUs or TPUs or something like that, and they can be updating the parameters. All right, so we have the algorithm. Now the problem that we're trying to apply this to is something like this. We have a state that is just a camera image over the shoulder, which is similar to the example we discussed before. So this is a not fully observable setting, but in this case, it was good enough. The action is a 4 degree of freedom post change in the Cartesian space plus the grouper control. So we can also close and open the grouper. And the reward will be binary at the end. So if the object was lifted, you get reward 1. And if it wasn't, you get reward 0. All right, some results from it. So first, there were 7 robots that were collecting data over the course of a few months, and it collected 580,000 grasps. And we were evaluating things on unseen test objects. So these objects were not used during training, and was able to grasp them with 96% test success rate. So basically, really, really good. It was also able to learn some behaviors that were not really in the training set that were necessary to grasp new objects. So this is, for example, a little construction where you first need to singulate the objects, and then you can grasp them. So it learned how to do that as well. It is also able to grasp objects such as that little ball, and you can mess with it a little bit, and it's a closed loop behavior. So it's able to track that ball and get back to it and try to grasp it again. And it is also capable of doing autonomous retrials where it's not able to grasp it and it fails a few times. It will know that it failed and it will try to do it over and over again until it gets it right. All right, so to summarize Q-learning, the big pros is that this is more sample efficient than OnPolicy methods. We can incorporate off-policy data, even including a fully offline setting where there are no robots or no agents that are collecting experience as we are training the policy or the Q function. And another important point is that we can update the policy even if we don't see the reward. So if you recall in the policy gradient case, if our reward was equal to 0, the gradient would be equal to 0. Here it's not necessarily the case. So even if you don't see the reward, that might inform your Q function. And it's relatively easy to parallelize, and this was used by the QT-opt in the QT-opt algorithm. In terms of cons, it's harder to apply standard meta-learning algorithms because it's a dynamic programming algorithm, not a gradient descent algorithm. And it requires quite a few tricks to make it more stable and to get it to work. Another argument that it might be potentially harder to train a Q function than to train a policy, but that really depends on the problem. All right, so this is a quick review of how Q learning works. So now I would like to talk a little bit about multitask Q learning. And I'll stay a little bit after the lecture to answer your questions because we're running out of time. All right, so in terms of multitask RL algorithms, we learned so far that we can easily transform our policy or our state to include the task indicator to augment the state by it, and then we can apply it to multitask RL problems. So we can do exactly the same with Q function, augment the state with a Z information that tells us about the task and keep going. And it's analogous to multitask supervised learning. So we can use all the tricks that we know from there, such as stratified sampling, different weight sharing schemes, and so on. However, there is something different about RL here. And the difference is that here the data distribution is controlled by the agent. So the fact is that in supervised learning, we had that data set that was curated and we could sample from it. Here we get to decide which task we want to explore. So one question that comes immediately to mind is, should we, in addition to sharing weights, because we are trying to learn a policy that can do multiple tasks, can we also share data between different tasks? And one little question I have to all of you is, why are we mentioning this now? Why are we talking about data sharing right now? And we'll get back to this question, so think about this a little bit. All right, so first a little example how we could reuse the data between different tasks. So let's pretend that we are trying to learn a hockey task, and there are two actual tasks. One is to do passing. We are trying to pass as well as possible. And another task, that's number 2, is to shoot goals. Now we can train all of these tasks, but both of these tasks, we can share weights between them. But now what happens if we accidentally perform a good pass when trying to shoot a goal? Right? So we're trying to shoot a goal, but it just happened to be that we did a really good pass. So one thing we can do is we can store that experience. This is a valid experience, but in addition to this, we can create a copy of it where we relabel that experience with another task ID. So pretend that this was task 2 and put the reward there for task 2 and store that as well. So basically it's equivalent to us saying that this was a plan all along, right? So I was trying to shoot it, I passed it, I was actually trying to pass it, and we'll try to store that experience as such. And this will refer to as hindsight relabeling or hindsight experience replay paired. All right, so how would that work in practice? So we'll collect some data using some policy. We'll store the data in the replay buffer. And then we can perform on the data, we can perform hindsight relabeling. So we can relabel the experience that we just received, and we can pretend that the last state was the actual goal that we wanted, right? So here we are changing the reward function. We have R prime instead of the original R that we had. And we said that the R prime is equal to the distance between the current state and the final state that we achieved. So we pretend that this was the plan all along, and this is what we did here. Then we store the relabeled data in the replay buffer. And then we update the policy using the replay buffer. So this is similar to a standard Q-learning algorithm, except we can now generate much more data because we can do that hindsight relabeling procedure. So are there any other relabeling strategies that we can think of? For example, we don't have to use necessarily just the last state, but we can pretend that any state during the trajectory could have been our goal state and use that as a potential relabeling strategy as well. And if we do this, then very often we can see that exploration challenges are getting a little bit easier because we're getting much more experience and we are getting kind of a curriculum of tasks that leads us towards the goal that we wanted to achieve. All right, so I ask you I think one slide ago, why are we mentioning this now, that the data sharing concept? And with the task of passing and shooting goals, we could use our experiences and relabel them, and if we get to achieve another task that we weren't trying to do, we can relabel them as such and just use the successes of these other tasks and learn from those as well. So let's consider two other tasks. One task is to close a drawer, and another task, so this is the final goal of that task, and another task is to open the drawer. So the final goal of that task would be the drawer at the bottom where that is fully open. All right, so now the question is, can we use episodes from drawer opening tasks for drawer closing tasks as well? And how does that answer change for Q-learning versus policy gradient? So please keep in mind that for these two tasks, let's just assume that it's impossible to succeed at opening drawer when you're trying to close it, and vice versa as well. So it's not that you can accidentally achieve success as we did before in the hockey example, but here you would rather be using experiences from opening the drawer task as something that you should not do when you're trying to close a drawer. Right? So we are not necessarily using just our accidental successes that we can get to when we perform a certain task, but we can also use them as potential failures. And now, how does that answer change for Q-learning versus policy gradient? In the policy gradient case, because it's an OnPolicy algorithm, and because of that specific equation that we wrote, how we estimate the gradient, if the reward for a given task is 0, that does not contribute to the gradient. The resulting gradient from that will be 0 as well. In Q-learning, however, if we see a negative that is even coming from another task, we can still use it, and it can still inform our Q function that that action in that state is not really good. So this Q-learning and off-policy learning can allow us to use negatives as well and inform us how to do things better by learning what not to do. All right, so how can we do multitask reinforcement learning with relabeling even if it's not a goal condition setting? It looks very similar, except for hindsight relabeling, we'll just relabel our experience according to some other task J. Right? So we initially were collecting data for a specific task. Now we can pretend that that task can be relabeled for any other task, for example, task J, and we'll just overwrite our reward with R prime instead of original R, where the R prime corresponds to the reward function of task J, so RJ here. The question here is, what kind of tasks should we choose? And we don't really know how to do this. So one way to do this is to just pick them randomly and relabel to random tasks. Another way is to pick tasks in which trajectory is more likely to get high reward. And there's multiple more recent papers that talk about it that I link here. Right. One more question is, when can we actually apply this relabeling? So first we need to know, oh, there's a question, how do you get reward for the other task? Exactly. So first we need to assume that the reward function is known and it's easy to evaluate. So we can just take a look at the state and evaluate it for different tasks. We also need to make sure that dynamics are consistent across goals and tasks. And we need to be using an off-policy algorithm. Although there are people that are trying, there is research that is trying to do this also for on-policy algorithms, but it's a little more tricky. All right, so I think we're running out of time, so I'll skip the results and the other example. But basically today we talked about the multitask reinforcement learning problem, how we can solve it with policy gradient algorithms, how we can solve it with another family of algorithms called Q-learning that are off-policy algorithms, and how we can use those algorithms to do multitask Q-learning, where in addition to sharing weights, we can also share data between the tasks, and we talk a little bit how that data can be shared across different tasks. All right, so there are many remaining questions still. So first, can we use a model in multitask reinforcement learning? What about meta reinforcement learning algorithms? We didn't get to talk about these. Can we learn exploration strategies in addition to learning tasks? And what about hierarchies of tasks? And we'll talk about these in the upcoming lectures. There's also many additional OREL resources. I realized that we went really quickly over a very large body of material, and it might be difficult to keep up and to understand everything about policy gradient, and especially about Q-learning, because we didn't talk in detail about it. So I encourage you to take a look at some of the resources that are available online, as well as the other class at Stanford CS330. Right, so thank you very much for your attention. And I'll stick around for a little bit longer if there are any questions.
I have a quick question on the hindsight relabeling, if that's okay.
Yeah, of course.
So the first one you showed, where you talked about the goal state, can you only replace that? Is that only if you happen to end up in the goal state for another task? Or I was kind of confused what was going on with the goal states and when you could relabel there.
Right. I think we went a little bit quickly over that. Yes. So you can just take the last state that you actually accomplish in that trajectory. Right. So our trajectory consists of all the states that we encountered, as well as the action that we took, and the very last state that we ended up in, and pretend that this was your original goal. All right. So this is a goal condition setting. So a goal is fully defined by the state, and you can just say that the reward for that particular transition, for that particular episode, assuming that you're trying to accomplish the state that you actually ended up in, is maximum. So in this case, because this is a negative reward, it would be 0. So we were just trying to relabel to the very final state that you achieved, and we were saying that this is the goal that you wanted to achieve. Does that make sense?
I think so. Yeah. Thank you.